Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is lecture 10. It's going to be a short one, but I want to try to get across two main ideas. So this is lecture 10, AMAT362, Probability for Statistics. So last time, if you recall, we went over mean, median, and mode. So, you can also think of the mean as being synonymous with this notion of E of X, which is the expectation of a random variable. X, or you can think of this as the expected value of X, with the idea that, again, X is some random process of numbers. You collect numbers from this process, and then you add them up together, and you divide by the number of observations you get. And then that value should be something that's close to this number, E of X. I want to go through and communicate one of the most important properties of E of X. This is sometimes called linearity of expectation. So today, linearity So this is a hugely important concept, but it's going to look pretty simple, and it's also going to motivate lots of sort of adjacent ideas. So let me provide for you the two basic versions that together constitute linearity of expectation. And I'll go ahead and comment on some of the ideas that this is going to make us consider. So there are two components. So first component is the fact that if I have a random variable X and I do some sort of scaling, so let's say I take numbers and I multiply them by 10, that's only going to change the expectation by multiplying by 10. Conceivably, if I also take a random process and I always add some number B or subtract some number B, then that's just going to translate the expectation by that amount. So written out using equations, this says that the expectation of AX plus B is the same thing as A times the expectation of X plus B. This is really useful because suppose you know, or you can recognize a situation like this, where you actually already know ahead of time the expectation of X. Instead of going through and recomputing it using this sort of shifted copy of X, you can just use the value already computed and then scale and shift that appropriately. Second key part is this, which is if I have two random variables, X and Y, and I consider the expectation of their sum, then this is the same thing as the sum of their expectations. This is going to motivate a really delicate question, which is, what is the sum of two random variables? We'll spend a lot more time on it, but we're going to start by just going through some simple examples, which shows like what it actually means to compute this sum. So it's going to be two questions. This will motivate. So question one is, suppose I have, instead of just some translation, but I have some function of a random variable, when is it true that the expectation of the function of the random variable is the same thing as the function applied to the expectation? When is it true E of G of X equals G of E of X. And I'll go ahead and give you a hint that says, not always. And the second question, which we'll consider right after considering that, is what does it mean to sum two random variables? And in particular, the question is, if I define Z to be the sum of two random variables, X and Y, how do I compute the probability of Z equaling a given value? So both of these are going to be delicate questions, which are going to motivate us for a good part of the semester. All right, let's go ahead and consider practical situations where we might need to consider question one, and in particular, understand a situation of where our item one is true. All right, so let me go ahead and consider an example. So suppose you're told that the average temperature in April is 10 degrees Celsius. What is the average temp in Fahrenheit? Well, we know that there's a classic formula for converting Celsius, Fahrenheit into Celsius and vice versa. So in particular, if I thought about how to convert Celsius into Fahrenheit, it looks something like this. So G of X, which is going to be my degrees measured in Celsius, is going to be something like 9/5 times X plus 32. And this is going to be the output of this. So this is my function G. So I take in degrees Celsius and it outputs degrees Fahrenheit. Let's make sure that this formula works. So first of all, when I say it's 0 degrees Celsius, we know that that means it's 32 degrees Fahrenheit. And when I say that water boils at 100 degrees Fahrenheit or Celsius, I know that that corresponds to, well, let's see, it ends up being 180 plus 32 equals 212 degrees Fahrenheit. So another way of thinking about this is to draw the graph of this function, where here I've got on X, my degrees measured in Celsius, but then on my Y-axis, I have my degrees measured in Fahrenheit. And I'm not going to make the scale look exactly alike, but 9/5, it's almost a slope of 2. But then I've got this huge shift by 32. So I'm going to say this is something like this. So there's my graph of G of X. Now, the whole process here in probability is that I'm looking at the month of April, and I don't know where this is. I mean, Albany sounds about right. Let's just figure out what G of 10 is. Well, that's going to work out to be 18, I think, plus 32. So that's 50 degrees Fahrenheit. Yeah, that seems like maybe a fair average temperature for Albany in April. But the bottom line is that if I, let's say, measure the high temperature on each day for the month of April, that's going to define a process which, at least measured in Celsius, is going to just ping back and forth between days, where perhaps the center of mass of this distribution, which we learned last time, was the expectation of T, or T I want to think of as the random variable measuring the high temp in Albany, New York, on days in April. And so I've just said that it ends up having a maybe center around 10 degrees Celsius. But the bottom line is every day generates, a random number. Bing. So I go from day to number, which corresponds to the temperature. And then I can feed that number through this function g. And so what does that do? Well, it ends up transporting these numbers through. Well, I can just graph them up here. So then I do look at each of their values up on this graph, but then I can project down. And this gives me another set of numbers where I have shifted up and scaled by 9/5, and I've added 32. So this gives me a new random variable, which I can call g of t. And so it kind of makes perfect sense that if I have a unique mean, and again, for random variables, those, when they exist, the expectation is unique. And let's say it is, it's here, this ends up being the mean. Then I can just look at its value under this map G, and that's going to tell me what the average is for G of t. So the fact is that if I want to look at the expectation of G of t, where I think of t as the random variable of temperatures measured in Celsius, then I can compute the expectation of this new random variable where I measure in Fahrenheit as follows. Well, it's the expectation of 9/5 times whatever my random value t is plus 32. This ends up equaling 9/5 times the expected value of t plus 32, which we just figured out ends up being about 50 degrees Fahrenheit. So there are other situations where this might come up. So for example, if I take my die, which is labeled 1 through 6, and I instead look at a die where I'm looking at it between 10 and 60, where I now just add a 0. So I now have 10, 20, 30, 40, 50, 60 as the values of my roll. If I want to compute the expected value of my new die, which has 10 times the previous, then it's enough to just go ahead and compute 10 times the expectation of the original die. So I'll just write that down as a quick example. So ordinary 6-sided die, each roll produces an outcome uniformly on 1 through 6. If I relabel my die to, let's say, I don't know, maybe I'll call it 0, 10, 20, 30, 40, and 50. And if I before called this role X, and I now relabel this and I call this Y, I can recognize that Y is the same thing as doing 10 times X, but then when I've subtracted 10 from the value. So now 1 goes to 0, 2 goes to 10, and so on and so forth. We already know, so if I want to, if my question is, compute the expected value of Y, the answer is relatively simple. If I remember that the expected value of X ends up equaling 3.5, it's the number halfway between 3 and 4 in this case, because it's uniform, then I can go ahead and just compute and say that, expected value of Y ends up equaling 10 times the expected value of X minus 10, which is 35 minus 10 is 25, which again works out to be, right here, kind of in the middle of these two distributions. So this is my E of X, and this is my E of Y. All right, now let me give you an example where you can't just use any old function and have this result be true. So here's a quick definition. So if I want to compute the expected value of an arbitrary function of X, where X is my random variable, so if X is a, let's say, again, we're working in the discrete setting, a discrete random variable, and G is some function of X, oops. Then I can compute the expected value, then Y equals G of X. I can compute the expected value of Y by taking the sum over all possible values for X, my random variable. Maybe let's call these little x. I can evaluate G on that and then take the probability that big X equals little x. Before I was using K because usually we were studying situations where the possible values was some integer, but that's not always going to be the case. So now I'm going to start using little x to indicate possible values for my random variable X. So that's the definition. So we can call this also the expected value of G of X. But it turns out to have roughly the same interpretation. I take my random variable Y, where I basically first generate a random number according to X, then feed it through my function G to get another random number. That's a perfectly well-defined random variable. But it turns out I can, again, compute the expectation of this new random variable Y purely by using the function G and the probability mass function for X. So again, this uses the PMF for X. All right, so let me show you an example where computing the expected value of that formula is not going to lead to the same answer. So as computing just G of the expected value. So this is an example where E of G of X is not equal to G of E of X. All right, so let's imagine that X is uniform on -1, 0, 1. So what does that mean? That means that if I write down my possible values, little x, and the probability that big X equals little x, well, I've got -1 with a third, 0 with a third, and 1 with a third. And so if I use my rule for computing expected values, I get that E of x is -1/3 plus 0 plus 1/3, which ends up equaling 0. Now, let's imagine instead of using this linear function, like where I convert Celsius into Fahrenheit, I look at a function that says, let's say, squares my value. So imagine I have, consider g of little x equals little x squared, and define y to equal g of x. So one of the properties that x squared has is it can map negative numbers and positive numbers to the same positive number, because -1 squared is the same thing as 1, which is the same thing as 1 squared. So if I write down the PMF for y, well, maybe I'll use little y. I'll say big Y, which equals g of big X. There's only two possible values, 0 and 1. And so it kind of makes sense that if I want to compute, well, what's the probability that big Y equals 1? So let me try to fill in the blank here. Probability that big Y equals 1. Well, it kind of makes sense that this should be the sum over little x such that g of little x equals 1. And then I take the probability of little x equaling 1. So if I apply this formula, that tells me that, well, obviously -1 goes to 1 underneath x squared. But then I also have 1, which goes to 1 underneath x squared. So this corresponds to, oh, sorry, let me correct this. So little x equals little x. Big X equals little x, where I know that little x now equals 1. So this ends up being probability of x equaling -1 plus the probability of x equaling 1. So this allows me to fill in this, this bubble here to be 2/3. So now what's the expectation of y? Well, if we use the formula I just gave you, it ends up being something like when you sum over possible values little x, and then I look at x times the probability, or sorry, g of little x times the probability of big X equaling little x. And this gives me, well, -1 squared times the probability of big X equaling -1 plus 0 squared times the probability of big X equaling 0 plus 1 squared times the probability of big X equaling 1. And this all together, you can just see, because that's a third and this is a third, ends up equaling 2/3. Yes, yeah, exactly right. So, and this kind of makes sense if you were to try to draw the picture. So imagine I've got my X, I've got my graph. Let me use green for my graph of little y equals g of x, which is x squared. And let's imagine that I've got my 3 possible values for big X, -1, 0, and 1. But if I map them up via this function and then push them forward, then I end up getting only 2 possible values for y. And because I can just add the probabilities, I now have something where I now have a 1/3 chance of 0, but a 2/3 chance of 1. And so when I compute the mean of this new distribution, I get 2/3. But notice here that so this 2/3 is equal to expected value of x squared, which is the same thing as my g of x. This is not equal to the g of the expectation of x, because the expectation of x is, again, 0 right here, right? Because you could just see uniform distribution, expected value is x, of x is 0. We know that 0 squared is 0. So g of 0 is 0, which is 0. So this is not equal to e of g of x. Now, it turns out that as long as we're looking at functions which are injective, we can actually do something where we have this sort of property be true. But in general, it's something you need to be cautious of, that these are different. All right, let's consider our next question, which is, what does it mean to sum two random variables? Well, let's start with a really, really concrete example. So here's the question. We want to, what does it mean to sum two random variables? All right, so we basically have x and y, and we're trying to define a new random variable, z. So basically the idea here is that you want to generate a random value from x and its distribution, you want to generate a random value from y, and then you're going to sum these guys, and that's going to give you your random value that defines z. It's easy to make mistakes in this sort of situation, so let's try to be really careful and see what are the possibilities and maybe a concrete problem. So first of all, you might ask, why do we even need to study two random variables? Well, there are often situations where you have an experiment and you want to measure two properties about your experiment. Maybe the most classic example of this is, suppose I go out on the street and I ask someone, all right, what's your height? What's your weight? And then those are two random variables. Now there's some correlations between these, which indicates that these two quantities are not independent, but still we can take those two quantities, sum them together and get something. So let's first consider that. So why do we study two or more random variables? Well, say we're interested in two properties. Associated to an experiment. one of the things that we're going to have to understand is, what does it mean to look at the joint distribution that governs our two random variables? So now I guess there are two observations here. So one is that correlated, and sometimes they're not. All right, so let's and let me just give you an example where you do need to worry about correlations, because that's going to constrain what your possible sums are. So if I look at, let's say, height and weight, I think we all intuitively understand that there's if I were to actually measure these properties, I would see that there's some linear relationship between height and weight. In particular, it seems really unlikely that you could find, for example, a person who is, I don't know, 7 feet tall, but weighs 100 pounds, right? This is not going to happen. So that indicates that if I try to consider the probability of an AND event, I really need to be clear on that. It's not the same thing as just multiplying the probabilities of this. So not likely. In fact, I dare say it's 0. But unfortunately, if you were to take, let's say, the probability of a 7-foot tall person, you can't just multiply the probability of being 7 feet tall with the probability of weighing 100 pounds. I mean, there are a lot of children, are 4 feet or shorter, and they weigh 100 pounds. And so, both of these numbers are going to be non-zero. But here we're going to have 7 feet tall and 100 pounds. And we're going to write this and using a comma. So this is going to be, equal to 0. Let's say 0 probability, whereas this is going to be non-zero. And so what I'm defining here on the left by example is this notion of a joint probability distribution. So here's a definition. The joint probability distribution P of x, y assigns to a pair of values, little x and little y, the probability that big X equals little x, and the probability that big Y equals little y. And it turns out we're going to need this when computing the sum of two random variables. But let's do an example of this joint probability distribution. So consider the following. So imagine I've got a hat. And inside of this hat, there are tickets with numbers on them. 1, 2, 3. And so the basic idea is I'm going to reach in, I'm going to grab a ticket out, and whatever that number is going to be my my first random random variable x. Let's say x equals number on the first draw. And let's say y is my number on my second draw. Well, let's consider two different situations, which are going to correspond to two different experiments. So imagine I do the draws without replacement. And let's consider what are the set of jointly possible values for each of these. Notice that whenever we're doing draws without replacement, at least in combinatorics, we like to use this choose notation. So we have three elements. We're choosing two out of a hat. And we know that there are 3 choose 2, which is 3 factorial over 2 factorial, 1 factorial, which equals 3 possible pairs of values here. And so let's go ahead and then write them down. My apologies. Here we have to actually take into account the fact that order matters here. So here, because we're recording order, we need to distinguish ordered pairs. So meaning if I draw 1 then 3, that's not the same thing as 3 then 1, because if I'm recording what is the value of x in this experiment, here I get 1 as my first draw and 3 as my second draw. Whereas here, if I'm recording what's my first draw, then I get 3 for my first draw and 1 for my second draw. So these end up being different things. All right, so now let's keep that in mind. And one convenient way for writing down this joint probability is to look at my possible x values, my possible y values. So I have 1, 2, 3. And then I'm just going to go ahead and write a table where I put the probability of that joint occurrence happening. So one thing is that if I'm doing without replacement, I can never draw the same number twice. So that means here, the probability of drawing a 1 and a 1, a 2 and a 2, or a 3 and a 3 are both 0. But other than that, everything seems to be uniform, right? So it seems like I've got a 1/3 chance of first drawing a 1 and then drawing a 2. I can confirm that. So probability of drawing a 1, 1, first, then 2. Well, there's a 1/3 chance of that times, well, now there's 2 numbers left, so there's a 1/2 chance of getting that. So it actually ends up equaling a 1/6. My apologies. This ends up being a 1/6. And by similar reasoning, you actually get that each of these occurrences have a probability of a 1/6, which makes sense because there are actually 6 different ordered pairs, and each of them are equally likely. Makes perfect sense because remember, the multiplication rule says that if I break it up into parts, then I take the number of chances for my first part times the number of chances for my second part, which is 3 times 2. So this implies there are 6 distinct events, or I should say outcomes. All equally likely. So this right here, this table, is the joint probability distribution for x and y. I can write it as this. I can say that probability of little x, little y is equal to 1/6 if x is not equal to y. But again, both values are in the set 1 to 3, and then 0 if x does equal y. That's my my joint probability mass function. Now, let's consider this game where I want to then consider the probability of, or consider the random variable, right? I take my 2 tickets out and then I sum their values. So now let's consider z, which equals x plus y. So, thinking about it, what are the possible values for z? Well, if you think about it, the smallest value for either one is going to be 1, and then assuming that the next other one's distinct, then it's going to be 2. So that leads us to believe that the set of possible values for z is 3, 4, 5. And so what does that give us in this situation? So for example, what's the probability that my sum is 4, for example? Well, I need to consider all the possible ways of summing to 4 using my two tickets drawn from 1 to 3. So this is the probability that, let's say, x equals 1, x equals 2, x equals 1, and y equals 3, plus the probability of x equals 3 and y equals 1, which is a sixth plus a sixth, which ends up equaling 2/6, which is a third. Now, what about the probability of z equals 5? Again, same sort of thing where x equals 2, y equals 3, plus the probability of x equals 3, y equals 2. And again, you get this sort of 6 and a 6. If you sort of stare at this a little bit, you can kind of guess what the general pattern is, namely that everything has probability a third. And the way that I can see these values is by looking at my 3 possible values here, which is 1, 2, and 3, 3, 4, and 5, where I'm summing along these diagonals, anti-diagonals. And so it turns out in this setting here that the probability of z equaling 5 is uniform, or z equaling 3, 4, 5 is uniform. So if I look at my little z, possible values are 3, 4, and 5. Each of these ends up equaling a third. Now let's consider a quick variation on this. So imagine, so this is again, it's uniform. what happens if we do the draws with replacement? So that means if I draw one, I put one back in, there's a chance I could draw it again. Now this actually enlarges our set of possibilities, right? So we've got now I have, all possible ij where I is from 1, 2, and 3, and j is in 1, 2, and 3. So that means there's actually 9 possible pairs, right? Let's just go ahead and convince ourselves of that. So my possible values for my first draw, my possible values for my second draw, 1, 2, and 3, 1, 2, and 3. And if I just count up and use this to denote my sample space, well, each of these intersection points is a possible outcome. And you can count, there's 9 possible outcomes. Each of them are equally likely, so this ends up equaling a 9th. Probability of each of these events ends up equaling a 9th. So here, under this assumption, I have a different joint P and F, namely probability of x, y equals 9th, as long as x and y are both values 1 through 3. Now, what's the probability of getting each of the different possible sums? Because now I have a situation where I could draw 3, 3 and 3, or I could draw 2 and 2. And each of these lead to slightly different outcomes. So now let's consider what's the probability of x plus y equaling, let's say, 5. Well, this corresponds to, I could have sorry, I confused myself a little bit here. Sorry, let's say the probability of x and y equaling 3. Well, I could have 1 and 2 plus the probability of 2 and 1, which ends up equaling 9th plus a 9th, so it's 2 9ths. And what's the probability of x plus y equaling 4? Well, I could have 1 and 3. I could have 2 and 2, because now I'm replacing it, and I could have 3 and 1. And so this is a 9th, plus a 9th, plus a 9th, plus a 9th. This is 3 9ths. And then a similar story applies for when I consider this next value. So this I already figured out was 2 9ths. I could do probability of 2 and 3 plus probability of 3 and 2. But then I've got situations like this where probability of x and y equaling 6, there's only one way that can happen, which is that I draw a 3 both times. And so that ends up equaling a 9th. So the long and short of it is that when I take a uniform distribution on the possibilities for each ticket, I have a wider range of possibilities. And in turn, I also have a weird peaking behavior where 3, I guess we figured out that 4, 5 is actually probably the most likely, and 6 is down is the least likely. So anyhow, we end up seeing this phenomenon where the probability of the middle outcome ends up being the most. But this is an observation which is going to build up to lots of different things, and we're going to explore it in class shortly. I look forward to seeing you soon.